Any questions about yesterday? Okay. Chapter 12 is going to be the end of the semester. So I talked to Dr. Kwan, and he's okay with that. If we have any days, any leftover days, we'll go back and review. I do have a review sheet of 80 some problems that we can do in class, as well as answer questions, because the final's going to be comprehensive over the entire semester. But let's not worry about the final exam until we get through the last exam. Okay. So what are we going to? We're going to do more reactions today. So we've already done we've done HCl, HBr, HI, H plus H2O, and then H plus in an alcohol. And those are all pretty similar mechanisms. The mechanisms we're going to do today are kind of similar, but kind of not similar, which means they're not similar. So we'll start with another reaction we can do, which is called bromination. And as we do a reaction, we'll talk about stereo and regio selectivity. And I probably won't get to going over that with sort of a stepwise, how do you determine if it's stereo or regio selective, but we'll do that. If we don't do it today, we'll do it on Monday when we get back. So bromination is when you add Br2 to a double bond. You can also do this with Cl2 chlorination. So if I take my double bond and I add Br2 to it, that's adding 2 Brs. So I'm going to end up adding a Br to one carbon and a Br to the second carbon. So our first question is, for bromination, what am I adding? 2 Brs. Okay. Now, because I'm adding 2 Brs, this reaction cannot be regio selective. So it's sometimes easier to remember when a reaction won't be regio or stereoselective than if it is. And if you either have a symmetrical alkene or you're adding a symmetrical reagent, it can't be regio selective. Because if it's a symmetrical reagent or double bond or a symmetrical reagent, adding the bromines this way and adding them this way gives you the same product because I'm adding the same atom. So bromination, you don't have to worry about it being regio selective. We will have to worry about whether it's stereoselective or not. Okay. So there is no Markovnikov or anti-Markovnikov addition, although that's not necessarily true. So what happens is this. When you do bromination and you have your double bond, what happens is the Br2 approaches the double bond. And remember that the double bond has the pi bond. And so what happens is that as the Br2 approaches that pi bond, the Br2 polarizes. So you have this negative charge, or well, it's not really a negative charge, but clouds of electrons that make up the pi bond. And when the first bromine gets close to it, it kind of becomes delta positive, and the other bromine then becomes delta negative. But that's only under the influence of that pi bond. And so then what can happen is that you can break the bond so that, in essence, you've added a Br plus, and then the other carbon has a plus charge on it. All right, I'm not going to fight with it. That's probably better anyway. Okay. So while it's not Markovnikov addition, it is. Because what I'm really doing is I'm really adding a Br plus to the double bond. And in the next reaction, I'll show you how we can see that. Because if we're adding two bromines, we don't know which bromine went where. Okay? So the bromine comes in, and it basically polarizes so that we add a Br plus to one carbon, and then the other carbon becomes a carbocation. But the bromine is big enough that it can actually sit over the two carbons. And the reason it does this is so that each of the carbons then can share in that positive charge. Bless you. So the bromine is large enough, and H wasn't large enough to sit over both carbons, but bromine is. So what you end up doing is making this triangular intermediate with these two carbons sharing the positive charge, because it's always more stable to delocalize a charge than it is to have one atom bear the brunt of it. So this then delocalizes the charge. And so we end up with this triangular intermediate. Then the triangular intermediate now sets up stereochemistry. Because once you have the triangle, the next Br minus comes in to add to one of the two carbons. And if it's a Br minus, it doesn't matter right now which carbon it's going to add to. But it cannot add from the top. It can't add from the top because the bromine is sitting there as part of the triangle. And so what the bromine does is it adds from underneath the triangle, and then we break the partial bond of the carbon to the bromine so that we end up down here with the bromine having added underneath and the other carbon, or the other bromine then having added above. And we'll talk about which carbon it would really add to in a minute, but it doesn't really matter what carbon we're adding it to at the moment. Okay, so the triangle blocks the addition. Now, I'm going to talk about this almost as if it was SN2. Right? This is almost like a backside attack of the bromine on either of those two carbons. So what we end up with then is 100% trans addition. So for bromination, the three things are you're adding Br2. It's not Markovnikov or anti-Markovnikov because it's symmetrical, but you are adding 100% trans. You're adding the bromines 100% trans. Right. So those are the three things. Everybody with me? So let's just write the mechanism, and let's use a cyclohexane ring, since cyclohexane rings have a tendency to throw people off. And let me go ahead and just do a cyclohexane. Why not? Let's stop. What's going on? me open it back up again. I pushed a button I wasn't supposed to. Now I got it in this mode. But it should be in that mode. Okay. So I already got all that. Okay. So I'm going to take cyclohexane. And again, any reaction with cyclohexane cannot be Regio Selective because cyclohexane is symmetrical. So I'm going to go ahead and add Br2 to it. So here's how you write the mechanism for this, because that might be important in the future. We're going to take a double bond. The double bond comes out and reacts with one of the bromines, and then the pair of electrons goes to the other bromine. That's how we show that polarization process. And so then our triangular intermediate would look like this. We would have the bromine bonded to both carbons and both carbons having a delta positive charge. This is called, and I didn't name it earlier, this is a bromonium ion, is the name of it. So now I've got my bromonium ion, and now my Br minus is going to come in, and it doesn't matter in this case what carbon it adds to. It's actually going to add to both. So my Br minus comes in, adds to the carbon from underneath. This pair of electrons goes to the bromine, and so I'm going to have my bromine adding underneath, and my other bromine have added from the top. So they have to be on opposite wedges in order to form that 100% trans product. So this is 100% trans. Now, is the reaction stereoselective? Well, let's think about the definition. The selective part means, are there two possible products of this reaction? And this is where I don't like the selective term, because remember yesterday I said selective is anywhere from 5149 up to 100-0. So are there two possible products? Yes. There are two possible products because the bromines could have added cis. Whenever we do a reaction, we have Markovnikov, anti-Markovnikov, cis, trans. So the cis addition is possible. However, we get 0% of it. But the term stereoselective doesn't make any difference between a majority and 100%. So in this case, do I have more than one possible product? Yes. Are they stereoisomers? Yes. What kind of stereoisomers are they? They're diastereomers because one carbon has the same configuration and the other carbon has the opposite configuration. So they are diastereomers, so this reaction has selected one of two possible stereoisomers as the major product, and so this reaction is stereoselective. So bromination can be stereoselective. And we'll get more into the, well, what do you mean can be? When will it won't? Maybe we'll hold off on that until next Monday. But this one can't. This one is because there's two possible stereoisomers. They're diastereomers. It has selected one. It has selected one 100 to 0, and that's all it takes. So this reaction is stereoselective. It is not Regio Selective. Because I added, this is a double whammy, because it's got symmetrical reagent and symmetrical alkene. So therefore, it can't. If either one of those is symmetrical, it's not going to be Regio Selective. Okay. So that's how we would go about bromination. So what am I adding? 2 BRs. There's no Markovnikov, anti-Markovnikov. 100% trans. And what we're going to find is anytime you have a triangular intermediate, it's always going to add 100% trans. So we're going to have a number of reactions that go through a triangular intermediate. Okay. All right. Everybody kind of with me? Because now what I'm going to do is now I'm going to change the reagent. I'm going to add a second reagent to this. So what I'm going to say is, for this, and I'm going to do, I'm going to set it up by doing cyclohexane the same way. So now I'm going to add Br2 and water. And this is going to form what's called a bromohydrin. Okay, so I'm going to add a little bit of bromine, but water's going to be the solvent. And so now if I look at my mechanism, I'm going to have my Br, I'm going to have my pair of electrons from the double bond come out to the bromine and form a Br minus. And so I'm going to form my bromonium ion as my intermediate. Because remember, the double bond is a nucleophile, and so it must react with an electrophile. Water's another nucleophile. The only electrophile in here is the Br plus that I can make. So I make this bromonium ion. Now, when I made the bromonium ion before, all I had was Br minus, so it had time to swing around the molecule and add underneath. But now when I form my Br minus, there's a water right there waiting to add. So the Br minus doesn't get a chance to go underneath the molecule and add because there's already a water there. And so the water goes ahead and adds. So we'll add the water to the bottom carbon this time. Since it's symmetrical, it doesn't matter. So the water comes in and adds, and then the pair of electrons goes to the bromine. The water added opposite the bromine, so if the bromine added on top, that means the water is on the bottom as an oxonium ion. So now I added a Br and an H2O trans, 100% trans. And then in the final step, we lose the H plus, so that in the end we form the bromohydrin, which is when we have a Br and an OH next to each other. So this is the bromohydrin. So all I did was add water as the solvent to this reaction, and now the water is the nucleophile. Still with me? So that's how we change the mechanism when we add water to it. And I could do the same thing with an alcohol, but normally we do it with water. So is this reaction stereoselective? Go ahead and vote. A for yes. Let's see, stereoselective. A, yes. B, no. We have 21 people, so we'll see how many answers we get. How sad would it be, wake up on 8 o'clock not to come to class, but then you're by your computer answering questions, but somebody is. 2 people are. Glad they value their participation points. Okay, has everybody in here answered? I should find out who it is and say hi, so on the next question. Freak them out. Okay. So 19 say yes, it's stereoselective, and it is. So what did I do? The other possible product would have the bromine and the OH adding cis. That's the other possible product. And it's 0%. This one's 100%. I've selected over 2 molecules that are diastereomers or stereoisomers, so therefore it is. It is stereoselective. So yes, it is stereoselective. Okay. Is it regioselective? No, why not? What? The alkene is symmetrical, but the reagent is not. Because I'm adding a Br and an OH, it's not a symmetrical reagent. So now let's make it a little more complicated by using an unsymmetrical alkene with the bromohydrin formation. So now all I have to do is just add a methyl group, and it becomes a different problem. So now if I go ahead and add this, if I add Br2 and water to that molecule, the mechanism is going to be the same. I'm going to add my Br plus first to form the bromonium ion. And now I have a problem. Where should my water add? Should it add to the top or the bottom? And let me do this with an acyclic. Let me do a similar reaction down here with an acyclic molecule. So let's say I take this alkene and I add Br2 and water to it, so that I form this intermediate. So I've got two methyls here, and I've got an H here and an H here, a delta plus there and a delta plus there. We'll call the carbon on the left A, the carbon on the right B, and now you're underneath the molecule and you're going to add. So which carbon are you going to add to? Are you going to add to A, B, or both? Everybody in here has answered. At least I gave them more of a question this time. Okay, so we've got a kind of a spread of answers. A, B, and both. Majority being B. Okay. I like to ask the question before we go through the explanation, just so that you can give me the two possibilities that are out there. So let's start with the most popular answer, B. If you answered B, why did you answer B? Ashton?
It's less sterically hindered.
Okay, it's less sterically hindered. Right. Sounds like a reasonable answer to me, that the water would add to B because it's less sterically hindered. If you said A, why did you say A? There's no right or wrong answer here. Well, there is, but you don't know it yet, so there is no right or wrong answer.
I don't know. I think it's just the way I thought it, but I thought it would be kind of.
Don't ever start your answer with that.
Is the hydrogen, like, or how the hydrogen gets to the ones with the most, the carbon with the most hydrogen.
No, that's good. So in other words, what you're saying is the BR, well, I'll paraphrase it for you. I might be giving you the benefit of the doubt, but that's okay. So BR plus is like H plus. And so if BR plus is like H plus, then maybe it goes by Markovnikov addition, where the BR plus adds to the carbon with the two hydrogens. So in the end, the OH, or the H2O might add to the other carbon. That's okay. And if we did, and I was actually we can go back and do that, and you'll see that actually that is part of the correct answer. That the Br plus is going to end up on the carbon with the most hydrogens. But the idea that the water can attack the least sterically hindered position is also valid. Anybody have another reason why they chose A? Let me ask a question. Is this delta positive charge here, we normally don't care about it, what its exact number is, and I still don't care about its exact number, but which carbon do you think has the greater positive charge? A or B? Which one's more delta positive? Carbon A or carbon B? Because they're not equal. Discuss. So what came up in your discussion? Yeah.
Would it be A? Because
What did I just say? Don't cut your answer. Don't cut your answer down before you give it.
so I think maybe the hydrogen in the methyl groups could kind of hold the positive charge away from the carbon, and so those carbons would be like a little bit negative, and that would make the carbon that's coming back in a little bit more positive.
Okay. Does anybody else have similar reasonings?
We kind of thought it the same way, but we kind of thought it the opposite way, because
Uh-oh.
the charge, the positive charge, would it be overall, like the like carbon A, would it not be as positive as B, because there's no other carbons to
So what we're getting at in both answers is we're kind of getting at if these two were carbocations, which one would be the most stable? Is what I'm hearing. Of course, I'm sort of twinging that to get us closer. So if I said, what kind of carbocation does C look like? Because I'm going to put it in quotes. If the plus charge was totally on A, what kind of carbocation would you call that? And again, whenever I ask that question, the answers are primary, secondary, tertiary. So what does A look like? What kind of carbocation? Tertiary? Do we agree? How many carbons are attached to that carbon with the plus charge? 3. So that one kind of looks like a tertiary carbocation. What does B look like? Primary. So the idea of the methyl groups being on A and being able to stabilize that positive charge is exactly what we've talked about before. That A looks more like a tertiary carbocation and B looks more like a primary carbocation. Now they're not, because the bromine's sitting on both of them, but A is going to have more positive charge than B does because of that ability of those methyl groups to stabilize that positive charge. And it's kind of weird to think of, because the methyl groups are kind of pushing electron density, but they're pushing electron density, but there's still a positive charge there. So there would be more positive charge on A than on B, because it looks like a tertiary carbocation, and B looks like a primary one. Does everybody kind of see that? No, that gets us closer to the answer, but that's not the answer of where water would add. Now, C is still less sterically hindered. I will agree with that. But your water, what kind of nucleophile are you? Strong or weak? Weak. So you're electron rich, but you're not like super rich. You're kind of like New York City rich, where everything's more expensive than it is here. So you're bound, though, to donate your electron richness to the most electron poor of A and B, because you're a neutral nucleophile. And so which one are you going to donate the electron density to? Which of those two carbons is the most electron poor? Which one has the greatest delta positive charge? A. So in this case, because it's a neutral nucleophile, it has no choice but to donate to A and to attack A. If you were a strong nucleophile, we could make an argument that you're going to go for the least sterically hindered carbon. Okay. Now, what does this sound like? Most positive charge versus steric hindrance. It kind of seems like we're back into what reactions? Change the E. SN2 and SN1. Well, we know it's not a service dog, because they don't do that. Some stray dog in the building. So, it sounds like SN1, SN2, right? What dictated an SN1 reaction? The stability of the carbocation, right? What dictates the SN2 reaction? Steric hindrance, or the rates. So that's kind of what we're back to. If you have a neutral nucleophile, the neutral nucleophile is always going to add to the carbon with the greatest delta positive charge. If it was a negatively charged nucleophile, you could make the argument that it's going to attack B because it's least sterically hindered. So we're back to kind of SN1, SN2. Neutral nucleophiles can only do SN1. Strong nucleophiles can do both, but they prefer to attack. They prefer SN2. So what's my point here? I have to think about that. What is my point? My point is, what I'm trying to do is to put the nucleophiles attack, which one it's going to attack, in the context of the triangle. It has to add underneath. We know that because when I do this reaction, I'm going to get the bromine and the OH trans 100% of the time. The mechanism isn't in question. If the bromine just kind of slid over to one carbon, then that means I'd have a pure carbocation. The water would add 50-50. And it doesn't. So that means the triangle has to be in place. So the water will always add then to the carbon that has the most alkyl groups. And the bromine will add to the carbon with the most hydrogens. So now we're back to Br plus, H plus, Markovnikov addition. Right, which is what Kristen suggested what seems like a half hour ago. So this reaction actually goes by Markovnikov addition if I broaden my terms. So Markovnikov only dealt with H. But if I broaden my terms and I say, anytime you add the electrophile to the carbon with the most hydrogens, that's going to be Markovnikov addition 2. And so I can broaden that out and say, oh, Br2 and water, my three things. Br, OH. How do they add? Markovnikov with the bromine adding to the carbon with the most hydrogens. How did they add? 100% trans. So notice the reactions are getting a little more complicated here. But not much. Taking them step by step. Now let's do this reaction to really show you that it would be Markovnikov by saying, you know what? I don't know anything about the triangle. I'm just going to treat the Br plus as a Br plus. And we'll do it with the bottom molecule. So I'll say, okay, let's go ahead and add the Br plus to the double bond. I have two possibilities. I could add the Br to, let's see, this was carbon A and carbon B. Let me go ahead and add the Br plus to carbon A. Let me add the Br plus to carbon B. Oops. Did it wrong already. Br here with the plus charge there. Br here with the plus charge there. If I do it without the triangle, where would the water add? Which one of these two intermediates is more stable? Intermediate A or intermediate B? Which one's more stable? B, definitely, right? Am I even allowed to draw A? No, because it's primary carbocation. But in real life, the bromine's bridging. So there would be a little bit of charge there, but not as much as what's on carbon A. So that means that the major product would be adding the water, then turning it into OH. So this would be two steps. If I added the water, then I'm going to form that product. So if we if I would have done this first and then said where does the water add in the triangle, it probably would have been a little bit easier to go back and look at the triangle and go, okay, now I see that this carbon has more delta positive charge because it looks like the tertiary one and the primary one looks like it's primary. And the reason I'm starting out this way of looking at the triangle is because we've got at least another 2 triangular species that we have to look at, and they all involve exactly the same principle. Actually, one of the triangular species that we'll deal with, I can make it make the nucleophile add to the more substituted carbon, or I can make the nucleophile add to the least substituted, the least hindered. So we need to understand this idea of how do we deal with the triangle, and that's how we deal with the triangle. If this is a neutral nucleophile like it is, it's always going to add to the carbon with the greater positive charge. Which one is that going to be? The most substituted carbon. Right? So, I mean, at this point in the semester, we're kind of doing the same things over and over again. Which is either good because it's like, oh, okay, I remember that. Or it's bad of like, I don't know what he's talking about. And what he's talking about is used like 5 other times, so we need to get that under control. So that's how we deal with a bromonium ion's Regio selectivity. So up here, if we wanted to complete that, the water would add to the top carbon so that the final product would have a methyl group. It would have the OH underneath, and it would have the bromine then, still 100% trans. So for this reaction then, and again, I'm adding the water in 2 steps. I'm adding the water, making the oxonium ion, losing the H+. So for this reaction that I just did here, this is the first reaction that is both regioselective, right, because it's Markovnikov addition in our broader context, and it's also stereoselective because it added the Br and the OH 100% trans. So you have to take stereo and regioselective one at a time. But we've done reactions that are neither. We've done them that are both. And then there's some that are each. Okay. And we'll hone in a little bit more. I've given you some of the ideas of if it's a carbocation, it's never this. If it's symmetrical, it's never this. And so we'll put those together a little bit more next week as we go through more reactions. Okay. If you got your chapter 11 problems already done and you wanted to jump on these, I think there are some problems in today's folder. Some of the reagents we haven't done yet, but some we have. They're basically like cyclohexane, methyl cyclohexane, dimethyl cyclohexane, and then methyl ethyl cyclohexene. Sorry, they're all cyclohexenes. And so each one of them, it's more, is it stereo, is it regioselective? And so we'll talk about those more when we get back. Okay. If you had any questions over break, you can send me an email. I can email you back.